Hi folks. We are now going to focus on linear functions as opposed to other types of functions that we've talked about so far, because we're learning about linear equations in this module. So now that we know what a function is, let's focus on linear functions. A linear equation in two variables, if we're going to use x and y as our variables, is an equation that can be written in the form y equals mx plus b. M and b are constants, so they're not variables, they're constants, and m is going to give us a slope, and b is going to give us our y-intercept. And we will focus on that more when we get to this kind of slope-intercept format. But for right now, we just want to be able to write an equation in this format, and if we can, then it's in a linear function. This is going to give us a linear equation is going to give us a graph that's a straight line. And because it's got a straight line, it's going to have a constant rate of change. And you'll see that in our examples below. Specifically, you can have a graph that's a straight line, but it's not a function. So a linear function is going to be a linear equation whose graph is not vertical. If you have a vertical straight line, then the graph is not a function. A nonlinear function is going to be a function whose graph is not a straight line. And we've seen examples of that in the previous sections. What makes it not a straight line is that the rate of change is not going to be constant. So let's look at a few graphs and decide if they are, first of all, linear or nonlinear. Are they a straight line or not a straight line? And then we'll decide if the graph is a linear function, a nonlinear function, or not a function at all. So let's look at these examples. Graph A, this is not a straight line. There's not a constant rate of change. So this is nonlinear. And it is, however, it is a function. It is a function. And if I do the vertical line test here, I never cross the graph more than once. So this is a nonlinear function. This example is a straight line. It is linear. And is it a function? Yes, it is. If I do the vertical line test, I never intersect more than one point at a time. So this is a linear function. Looking at example C, this is a straight line. It is linear. However, this is not a function. If I do a vertical line test, here when x equals -3, I intersect this graph in many more than just one point. There are infinite points at here using the vertical line test. So this is linear, but it is not a function. Looking at example D, this is a straight line. So this is a linear graph. But this is, and this is also a function. If I do the vertical line test, I never bump into this blue line more than one time. So this is a linear function. Students sometimes get confused when they see a graph like E, because there are straight line aspects to the graph, but it is not a straight line graph. This is not a straight line. You could talk about specific regions being straight lines, but this is not a linear. This is non-linear, not a straight line. And then with the, in terms of a function, if I move my vertical line across this graph, I never bump the graph more than once. So this is a function. For part F, this is nonlinear, just like the previous example. There's not a single straight line here. This is kind of a composite of a couple of straight lines. And this is also not a function, because if I move my vertical line somewhere like here, then I bump the graph more than once. Now, from a graph, it's pretty easy to tell if you have a straight line or not. But what about if you have a table or an equation representing a function? How do you know then whether you have a linear or a nonlinear function? This is where that definition of linear functions have a constant rate of change comes into play. And so what we're going to do is we're going to look at the change in x as we look at each input and output value. Going from 3 to 6, that's adding 3. Going from 6 to 9, that's adding 3. Going from 9 to 12, that's adding 3. So every time we add 3 to our x value, what happens to our y value? In this case, we subtract 6. In this case, we subtracted 6. And in this case, we subtracted 6. This is an example of a constant rate of change. When x goes up by 3, which it does here 3 times, y goes down by 6. So this is a constant rate of change. Therefore, this is a linear, and it's a function. It's a linear function. You don't see any repeat x values. Linear function. Yeah. Let's look at example B here. What happens to x? What happens to x? What happens to x? It looks like we're increasing by 2.5 with each step. 2.5 with each step. What happens to the y value in each step? Let's see. At first we add 7, and then we add 11, and then we add 15. So even though our x value is going up by a fixed amount, our y value is not going up by a fixed amount. It changes. This is not a constant rate of change, because sometimes it goes up by 7, sometimes 11, sometimes 15. So this is non-linear. Non-linear. It is still a function because I don't have any repeat x values with different y values. So this can still be called a function. Let's look at equations now. Remember, linear functions can be written in the form y equals mx plus b. So the question is, with how these equations are written, can I write them in this form? Well, with this example, y equals mx plus b, here I'm getting 3.8 with no x. So to get no x, m must have been 0, because 0 times x is 0. But then my 3.8 could have been my b value here. So I can get y equals 3.8 from this y equals mx plus b format. So this one is a linear function. This example here, there's a square root. There's nothing about my y equals mx plus b that has a square root in it, so this is nonlinear. Similarly, this has an exponent in it, with x being the exponent, and there's no way, there's nothing in my y equals mx plus b that's raised to the x power. So there's nothing I can do to this equation to make it look like that equation. So this is also nonlinear. Looking at option D, y equals 2 over x. Remember, when x is in the denominator, when it's in the bottom of a fraction, that's not the same thing as x. The graph of 1 over x actually looks like this, which is definitely not a straight line. So here we're going to call this nonlinear. Here in this example, I've got some parentheses here. It looks like I can do the distributive property like that. So I'm going to simplify the expression on the right-hand side of the equation, see what I get. 6 times x is 6x minus 1. So 1 times 6 is negative 6. And that gives me 6x minus 6. That is in the format y equals mx plus b. So this is a linear function. Lastly, I have x squared minus y equals 0. This x squared component, there's no x squared over here. There's no kind of like term similarity between this and my y equals mx plus b format. So this is a non-linear equation. Let's look at kind of some real world examples here. But before we look at real world examples, I'm going to be talking about discrete domains and continuous domains. And discrete domains are going to be input values that consist only of certain numbers. Only certain numbers. So an example of this would be something like, it's the story problem we're going to do together. It talks about buying tickets. You can buy 1 ticket, you can buy 2 tickets, you can buy 3 tickets, but you can't buy 1.5 tickets. So this is going to kind of determine what kind of domain our graph has. Like you see here, integers from 1 to 5 are discrete, gives a discrete domain. But if we say all numbers between 1 and 5, then we can pick any kind of half number or third of a number that exists between 1 and 5. And so that will kind of affect what kind of solutions we can get from the problem. So let's scroll back down and look at this example. Museum tickets cost $15.95 per ticket, and each customer can buy a maximum of 4 tickets. Write an equation to express the total cost of buying X tickets. So slope-intercept form y equals mx plus b works well when you're writing linear equations that have a rate and a starting value. Okay, so here my rate is $15.95 per ticket. I know this is my rate because it mixes units. Rates always take 2 different units like dollars and tickets and put them together in a single quantity. $15.95 per ticket. Another example would be something like miles per hour. That takes miles, a distance, and hours, a time, and combines them together in a single value. So here, museum tickets cost $15.95 per ticket. That's my rate. That's going to be my M value. I'm going to have to multiply that times the number of tickets I actually purchase. And then I need to add in any starting value I have. Now, in this case, there is no booking fee or anything like that. Some websites might have a booking fee, like a flat fee of $5 to do an online order or something like this. This doesn't have one, so my kind of starting value is just 0. And this is going to give me my total cost, which is Y. So my total cost of buying X tickets is represented by this equation, which of course I can rewrite so that it doesn't have that 0 there anymore. Now, find the domain of the function. Is the domain discrete or continuous? Explain. Well, as I already said previously, you can buy 1 ticket, you can buy 2 tickets, but you can't buy 1.5 tickets. And here we're told that we can buy a maximum of 4 tickets. So what are my options here? I can buy 0 tickets, I can buy 1 or 2 or 3 or 4, but 4 is the maximum. So in terms of my domain, those are the values that I can have, 0, 1, 2, 3, or 4 for my domain. Graph the function appropriately. If I'm going to graph this function, I need to know what points to put on the graph. And since I know that my values for X can only be 0, 1, 2, 3, or 4, then those are going to be the values that I test. And what I'm going to do is I'm going to plug each of these values into my equation, y equals $15.95 times X, to get an output value, to get my Y value. So 0 times $15.95 is just 0. 1 times $15.95 is just $15.95. 2 times $15.95 is $31.90. 3 times 1595 is 47.85. And 4 times 1595 is $63.80. So what I have here is a bunch of ordered pairs that can help me plot the points on my graph. So I'm going to have 0, 0 is one of my ordered pairs, which I'll plot right here. I'm going to have 1, 15.95 as another ordered pair, which will be about here. I'm going to have my next ordered pair is going to be at 2, 31.90. 2 and 31.90 will be around there. 3 and 47.85 comes in here. And 4 with 63.80 plots in about here. Okay. Now, if this were a continuous function, I would go ahead and draw in a straight line here, but this is not a continuous function. My only choices are to buy 0, 1, 2, 3, or 4 tickets. And so it is more appropriate to leave these as separate dots and show the graph this way. Let's look at one more example. An anteater consumes about 35,000 insects each day. Write an equation to express the total number of insects eaten as a function of the number of days. So I want to know the total number of insects eaten in terms of my kind of y equals mx plus b. So let's see, y equals mx plus b. Remember, m is the rate. And here's my rate because it's 35,000 insects each day. So I talk about insects and day in the same value. So that's going to be my rate, 35,000 times x. I'm sorry, not times x because this is the number of days. So I'm going to erase that x and use the letter D instead. Plus b, plus some sort of base value that I'm starting with. Like if the anteater had already eaten 200,000 insects that week, and I was adding on to that. But that isn't true here. I haven't kind of given a starting value for the number of insects the anteater has eaten, so this is going to be 0. So we'll just have the function n equals 35,000 times d. Find the domain of the function. Is the domain discrete or continuous? Explain. Well, the domain is based off of this independent variable over here, the number of days. And although we count days as being, 1, 2, 3 days, it is possible to eat insects for half a day or for 3.75 days. You can have fractional days. So a continuous domain is more appropriate here for that reason. So how are we going to graph this function? Just like before, we're going to input some x values and get some output y values and plot those points on the graph. There's no reason not to pick nice, easy, round numbers for x since we're just going to kind of plug them in there. So let's just say 0, 1, 2, 3, and 4 for different values for x. And what output values do we get when we plug these in? Well, if we plug 0 in for D, 35,000 times 0 is just 0. If we plug 1 in for D, and in fact, it would be more appropriate for me to write D here and N here. Okay. Plug 1 in, 1 times 35,000 is 35,000. Plug 2 in for D, and 2 times 35,000 is 70,000. Plug 3 in, 3 times 35,000 is 105,000. And if you plug 4 in, you get 140,000. 4 times 35,000 is 140,000. So we've got our ordered pairs now. We're going to graph the point 0, 0, 1 with 35,000, 2 with 70,000, 3 with 105,000, and 4 with 140,000. Now, this graph is not pre-labeled for us. We're going to have to label it ourselves, and we're going to want to choose a sensible scale to capture all the points we want to plot. The smallest value we have on either axis is 0, 0, so we'll just kind of draw the vertical y-axis and the horizontal x-axis and call this 0 on either side. Our independent variable goes on the x-axis here, so this is going to be the number of days. And we kind of want to use up as much of the graph as we can, so we'll just go ahead and say this is 1 day, this is 2 days, this is 3 days, this is 4 days. You want to label kind of a sensible number, you want to have sensible spacing and also have sensible number labels down here. Don't pick a bizarre quantity like 37. Pick numbers you can easily skip count, like you can count by 1s, you can count by 2s, you can count by 5s, you can count by 10s. So looking at the y-axis here, we need to be able to go all the way up to 140,000. So how to do this is a little trickier. I need to be able, so if I rounded that off to 150,000, let's see, I could maybe do, let's just call this 50,000. And then this one would be 100,000. And then this one would be 150,000. And then this one would be 200,000. So I'm counting up by 50,000, and that's appropriate given how big my numbers need to get. Now I'm ready to plot my points. I have a point here at 0, 0. Oops, different color here. I have a point here at 0, 0, and then I have a point at 1 and 35,000, which is going to be around here. I've got a point at 2 and 70,000, and 70,000 is going to be about here. I have a point at 3 and 105,000, which is going to be about here. And then I have a point at 4 and 140,000, which is going to be about here. Now, because this graph is continuous, it is appropriate to connect all of these lines together, or all these points together. So I'm going to do my best to draw a straight line here. Apologies in advance for the crookedness. I'm sorry, I forgot a really important thing. I did not label what these numbers on my y-axis mean. This is the number of insects eaten. Okay. Because part of drawing a good graph is labeling those axes with words and units. So when you draw a graph, make sure that you are consistent with your scales. I decided that each 2 marks was going to be 50,000, so then I was consistent with that. I added another 50,000 to get 100,000, then 150,000, then 200,000. On the x-axis, I decided each 2 marks was going to represent 1 day, and then I was consistent about that spacing. I labeled those values on my x and y axes, and then I also labeled my axes with words. So this is how you can kind of draw a graph from scratch if you have an equation for drawing, an equation to plot on the graph. I hope this helps.